That's good. That's good. All right. Well, I think everybody, we're going to get going here. And as per our normal approach with these Zoom presentations, I'll probably mute everybody initially so that as we go through, we don't have any kind of background noises or what have you. There's a chat feature at the bottom of your screen that you can certainly type in a question if you have as we're going through. Rob Ellis from FIA will be monitoring that as well. And then obviously at the end, what I'll do is I'll ask, when we finish the presentation, if there are any questions, we'll open it up and just unmute yourself and fire away, see if we can answer any questions that anybody has. So without any further ado, we'll just kind of jump into this if that's all right with everybody. Let's see here. So again, my name, George Carey. I work obviously here at FIA, and this morning's presentation is just a very specific subject matter having to do with expansion tank sizing, and just kind of the behind the scenes of what's really going on with an expansion tank, and what it does, why we need it, how it's properly sized, etc. There's just a lot of, I don't know, misnomers or misunderstandings sometimes within the industry with expansion tanks and how to properly select them, what are their purposes, where to locate them, etc. So that's what we thought we'd speak to everybody this morning about. So we're going to get going. At the end, like I said, we'll open it up to questions, and as well as we'll have a follow-up email thanking everybody, providing a certificate, and also probably a copy of this presentation, and then some other technical articles that I have written myself on expansion tanks over the years. So, as I say, in the heating industry, in the beginning, we're kind of in a unique spot. Everyone that's here in the New England area, most of the steam and hydronic systems all originated right here in the Connecticut, Boston, area. So we were kind of like the testing grounds, if you will. They almost like a testing lab. Literally, a lot of this stuff was, they were kind of guessing as they went along the way, if you will, some of the heating engineers and installing contractors, etc. So here's just a picture of an old gravity hot water heating system with a coal-fired boiler. And just pointing out to the top right here, even then in the gravity systems, they knew they needed an expansion tank to support the expanding water so that you wouldn't build too much pressure and blow a relief valve of some sort. Even those relief valves back then were pretty questionable as far as the integrity or the capabilities. So very subtle system, gravity hot water. Obviously, you fire this coal-fired boiler, you've got to get water to circulate to every radiator in that home, or you don't get paid. So here's just a kind of a quick picture of what you might see. And I don't know if you guys have ever had a chance to see some of these older open expansion tanks, typically up in the attic, the highest point in the system. Most times on the top of the tank that have this vent/overflow. So if for some reason there was an overfill of water, it would be coming out over this overflow pipe. But more importantly, it acted like a vent. And there were no air separators back then, but the velocity of the water was so slow that the Mother Nature would just kind of take over, and the buoyancy of the air bubbles would slowly work their way to the high point and find their way, into this tank and then out through the vent line. A lot of times these tanks would have a gauge glass just to indicate, because they wanted to make sure if they knew if they had water at the high point up here, then all of their piping and their radiators would be filled with water. So that was another use for this open style expansion tank. I had the good fortune a few months back, before all of this craziness arrived, Mark Lundquist, a salesman for FIA, and myself, we were looking at a mansion, an old 100-plus-year-old mansion down in, I think it was like northeastern Massachusetts. And anyways, contractor's taking us through the whole house after we come up with some plans for the renovation. And he took us up to the attic. And here, and lo and behold, it's not active, it's not connected, but here was the old expansion tank. And they would have had an overflow pipe up the top here that went up through the roof. So not unlike that guy right there. And I commented to the contractor, it's kind of funny, but when they're made out of galvy, they typically just disconnect them and they let them sit there forever. When they're made out of copper, they disappear fairly quickly and make their way to the junkyard to get some money. But anyways, here's a picture. So it's not uncommon. You find some of these older homes, you might see some of the remnants of an old gravity hot water or an old steam system, what have you, some of the different components. And just another example of this was quite an invention back then, back in the day, because now we actually had a cold water line that automatically filled the system from the high point with this ball cock. And as long as the ball cock was at a certain level, the valve was closed, and if it started to drop down, the valve would open, reposition, and add some makeup water to the system. But that was kind of like an ingenious thing, basically about 100 years ago. But again, another open expansion tank. In this case here, the overflow wasn't going out the roof. It was actually coming down this line here, down to probably like a slop sink or a drain in the floor down in the basement. So going from an open tank to a closed pressurized tank, it was very interesting. I did some research on the history of how this all evolved. And it's pretty ingenious, actually. Some of these heating engineers back then were very, very talented people, very ingenious, if you will. So the industry, the hot water industry, was looking for a better way to control the firing rate of a coal-fired hot water boiler. Now think about that. How do you control the firing rate of coal-fired boilers? And so they looked to their brethren, if you will, to the steam industry. And how were they handling this? And the steam industry, steam systems, steam manufacturers, they come up with this diaphragm damper regulator. And you're not going to see this out in the field anymore, obviously, but every now and then you get into some of these older homes and you might look up in the ceiling and you'll see pulleys, just the remnants of what was left over of a pulley. And that's just letting you know that they had some type of device like this probably back, again, it's probably going to be a 100-year-old home or maybe even a little bit more. But what they would do with this diaphragm damper regulator is, as the firing rate was increasing, so the pressure was starting to build, and the regulator would sense that, it would reposition, this arm would reposition through these pulleys, and you would start to close the damper. And as you close the damper, you started to starve the fire of air. So the firing rate started to be reduced. And as it reduced, the pressure would start to drop. And as the pressure dropped, this arm would reposition accordingly. And all of a sudden, the pulleys in the chain would pull the damper open, increasing the firing rate. So it would kind of subtly just go back and forth between an increase and a decrease, which was changing the firing of this coal-fired boiler. So the hot water guys were like, how can we do something like this? Well, there was a company out of St. Louis, Missouri, D&T, and they came up with the first closed pressurized expansion tank. Technically, it's a compression tank, but the industry's just always accepted the terminology expansion tank. But with this little diaphragm regulator over here, and again, some pulleys and chain, they would influence the opening and closing of the damper to increase or decrease the airflow, which meant increase or decrease the firing rate of the coal-fired boiler. So that was the beginning of a closed expansion tank. Eventually, they added booster pumps to these gravity hot water systems. And this allowed, obviously, and that was where the expression came from, booster. They were boosting the heat out to the system faster than just simply by gravity. When they closed the system, minimal makeup water was needed, so it was kind of a truly closed, inert. The water wasn't aggressive. The oxygen had been burned off. And with that closed system, you could actually run some higher water temperatures. Instead of being open to the atmosphere and being concerned about flashing the steam, now with a little bit of pressure, you could run higher water temperatures. The benefit to that was the hot water guys back in the day could now start competing against the steam guys, and they could provide higher water temperature, which meant smaller radiators. So it was a competitive situation. So it was very interesting how this whole thing evolved. And this all took place right here in the New England area. So as you get into expansion tanks, as they evolved, the first system that really became very prevalent within the engineering community and was installed all over, the Northeast here, was a system called air control. And it was developed by Bell and Gossett. They were big proponents of this air control system. So whenever you walk into a basement or whatever, and you see an old steel tank that's still active, one of the things you want to make sure is that within that system, there are absolutely no automatic air vents, because an automatic air vent has a very small brain, and his job is, if I see air bubbles, air, volume of air, I displace it, I get rid of it, I vent it out. The problem with that, with this type of system, was they didn't want to vent any of the air. They just wanted to control it and direct it up to the steel compression tank or the steel expansion tank. And they had a whole mechanism, a whole system of components that would work together to do that. And those systems were actually, pretty effective, very effective actually, if they were installed correctly according to installation manuals. So whether it be here, a little residential boiler with a boiler troll fitting and a collar, and there's a dip tube that you can't see inside here that's kind of forcing this circulator, if he's turned on, because the thermostat upstairs is calling for heat, the water has to get down through the dip tube and up into the suction of the pump and out to the radiation. But the velocity in this wide spot in the river is so slow that the air bubbles that are released when the boiler fired would gather at the very top, enter into this collar, and be directed up to the steel compression tank. Here is just a commercial version, perhaps, where maybe we're using a roll air troll, which is pretty common in larger systems, larger heating systems. And instead of having a vent on the top of this like we do typically today, they would just pipe, again, the line to feed that steel compression tank. So that was very popular, air control system. Some limitations to the system and why the diaphragm and the bladder style, which we're going to get into next, why that kind of took over, was one, the tank had to be installed at the high point. It always had to be above, so that you could use Mother Nature and get those air bubbles that were being released directed up to the bottom, to that tank fitting, that air troll tank fitting, and enter into the tank. So it was heavier, had to be supported from typically the cellar ceiling, the joist, sometimes between the joists, and it was just physically a bigger tank because there was a mixture of air and water in this tank right from day one, right? As soon as you attach it to the system. And it's just the way they worked. The other, kind of downside, if you will, was the air and the water could see each other. So as the boiler turned on and off, well, the water temperature would change. So air can come in and out of solution based on the temperature and pressure of the water. So when the system was off, some of this water perhaps could absorb some of that air. It might migrate through. This tank fitting was there to try to prevent that, but it could happen. So there's just, it was a little, got to dot your I's, cross your T's type of, techniques that you need to pay attention to. One comment here, keep sight glass valves closed. Sometimes on these bigger tanks, they might have, I don't know if we got a picture one, I'm not showing it. They might have a gauge glass. And if you have a gauge glass, it's to indicate the level. The bottom portion of that gauge glass, that valve assembly, is going to be seeing water all the time. But the top portion is, generally speaking, is not. And the concern there, and why they make this statement, is the gasket, if you will, the packing of that valve dries out, and all of a sudden it's a leak path. And so now, as the system is under fire and it's building pressure and the water's expanding in here, it can push this air out that packing of that dry valve. And in doing so, it drops the pressure, more makeup water comes in. The only place the makeup water can go is into the tank. And eventually you have a relief valve back at your boiler plant that is, discharging. And you walk in and the tank is flooded. It's filled with water. There's no more spring. There's no more volume of air. So they'd always say, if you want these gauge glasses and the valves, make sure they stay closed. Again, like I mentioned earlier, definitely do not use automatic air vents. And when they do log, the relief valve will discharge. Here's just a quick picture of that air troll tank fitting. And, it's it's days, unnumbered. The system, all of our design systems, we moved away from this technology, but it was pretty ingenious, if you will. The way they would size these tanks, they were starting with a standard of like 45, 45% of air and water. And the way they would establish that on commissioning the system is by using this fitting, this air troll fitting. Back up here. The diameter of this tank was very important. And based on that diameter, that's how you would buy that particular air troll fitting. And you'd have these two tubes, a tube within a tube. And there's this little fitting down here at the bottom, an air vent, and that you would open on initially commissioning the system. And as water is moving into the tank, it's venting air out of the system, out of the tank and down through this air troll fitting. Once the water line got high enough that water started coming out this vent line right here, this little air troll vent valve, you'd close it. And then the remaining part of that, as you're filling the system, that air would get compressed. So you started off with the appropriate relationship of air to water. And the purpose of that fitting, just real quickly, was to prevent gravity circulation. You were trying to keep as best as possible the air that was in this tank, even if the water absorbed it, you didn't want it to gravity drain out of here and then release that air into the system. So that ATF fitting tried to prevent that. Showing a quick picture here, I always get a kick out of this. It's a couple years old now, but here we're showing a couple of high efficiency, 95% efficient lock and bar boilers, modulating condensing boilers that were specified by an engineering company. And that same engineering company specified an air troll, an air separator, an air scoop from B&G, and an air troll tank fitting, and an ASME compression tank for this, commercial job, this commercial application. And I kind of, it makes me laugh or smile a little bit in that here we are embracing the latest and greatest in terms of high efficiency condensing boilers to heat a building. But the engineer, probably an older gentleman, brought up in this school of air control, still specified a compression tank with an air troll fitting and an air separator. So kind of the clash of two technologies. Someone sent me this picture. This was kind of interesting. This is a boiler room, and what you can't see, you just see these air troll fittings right here, but there are 3 expansion tanks that were concealed. And the boiler relief valves were constantly blowing, and the water tanks were just, the compression tanks were just constantly waterlogged. So it's kind of difficult to maintain those tanks when you put when you enclose them in the ceiling. So the other method, which is what we use on a day-to-day basis today, is called air elimination. It was originally introduced to the industry through a company called Amtrol, right down in Cranston, Rhode Island. And they were the first company to kind of bring over bladder or diaphragm style tanks to the United States. Obviously, they're a big name and been around a long time. But their method was completely different. We're going to use an air separating device, but now we want to vent all of the air that this air separator catches and get rid of it, because we're using a diaphragm or bladder style expansion tank that already has air in it. We don't need to redirect the air that came out of solution up to this compression tank. It's already there. So just get rid of it. So it's called air elimination. Very, very common residential application right here, showing an air separator and with a high capacity vent on the top. So any of the air that gets released from the water is heated at the boiler here, comes up through this air eliminator or air separator and gets vented out of the system. Here's my expansion tank, my diaphragm expansion tank. It's got we'll talk a little bit about it, but it's got a butyl diaphragm inside here with an air charge on the other side. The air and the water don't see each other. Another benefit to this technology. I don't need to mount it up in the attic or, up in the ceiling or anything like that. I can put it really almost anywhere I want. Here's a picture on the right-hand side of a commercial application where I have a air separator, a commercial roll air troll. And here I tie in the line to my bladder style expansion tank. So you can put them almost anywhere, physically smaller than their older steel compression tanks because there's no water in the tank until such time that you start heating the water with a boiler or whatever your heat source is. So they were able to be, they're physically smaller than a steel tank, and you can put them almost anywhere in terms of physically located. So they refer to them, sometimes they call them pre-charged tanks. And what it means is pre-charged, they're filling the tank with compressed air before connecting it to the system. We'll spend a little bit of time on that. Tank must be pre-charged to the cold fill pressure. Most tanks, commercial and residential, they're going to come typically with a 12-pound pre-charge, but it's not necessarily the magic number for all systems. So one of the takeaways of this little presentation this morning is recognize this. When I'm dealing with a diaphragm or a bladder tank, and I want to pre-charge it to match the cold fill pressure. What's the PRV? What's the pressure reducing valve setting to fill your hydronic system with water all the way from the bottom to the top? And I want to make sure that that tank's pre-charge matches that. When I buy a tank at a wholesaler's place of business, when I buy it, it's going to be pre-charged to 12. A lot of applications, we'll get into it, enter into a two-story home where 12 PSI is appropriate. But if you're going into something other than that, 12 pounds is not the right setting. The other thing is the Department of Transportation, the DOT. They don't want these manufacturers of these tanks shipping these tanks pre-charged any higher than, I think it's 15 PSI, but most manufacturers standardize on 12. But you want to make sure, this is a big takeaway right here. Tank must be pre-charged to the cold fill pressure. Kind of a couple of cutaway looks of the two different tanks. One's over here on the left is a bladder. And so what's going to happen is when you connect that to the system, this bladder is actually is shrunk, if you will. It's compressed. It's very small. And it's the air that's sitting around here that's compressing that bladder. And then they'll have this hose or this tube, and the system water, as it expands, enters into this tube and starts to fill the bladder. And in doing so, it's squeezing the air, which means it's increasing the system pressure. A diaphragm has a butyl diaphragm rubber separating the air from the water. Typically, they're not full acceptance. A lot of times, bladder tanks can be full acceptance. But the system water that's connected right here is going to be entering into this tank, squeezing the air by extending that butyl diaphragm to a certain point. And we'll get into that when we start talking about sizing them. But that's a very common, these two guys are very common commercially, as well as a diaphragm tank, residentially speaking. They ship them at 12 PSI, but it's not necessarily always the right number. Here's another good cutaway. This is showing a bladder again, full acceptance. So here's the bladder, kind of starting to fill up, if you will. Normally, it's kind of the air. Once you pre-charge it, you're going to squeeze that bladder until such time that the heated water enters into that entrance right here, that's connection, and then down that hose or that tube, it starts to fill the bladder. Here's a diaphragm cutaway, both the bottom and the top, and somewhere there's a connection point. I think it's right along that ridge right there where this butyl diaphragm is connected. And the point of this picture, which is pretty cool, is this is how they come out of the box, right? They got a pre-charge, the diaphragm is extended. When you connect it to the system, you connect it to your hydronic heating system, and the system is cold, we really don't want any water in this tank. And the way that works is back to that statement. The pre-charge of this tank matches the pressure reducing valves setting to fill the system. So as long as they're equal, water is not going to enter into this tank. Now I have all of this expansion area to accept my heated water as the boiler comes on, fires up the heated water. And that's the purpose of a diaphragm tank. It's not to have cold water, system water in here, because if you were to make that mistake and have a higher fill valve versus a pre-charge, now I'm going to have cold water enter into this tank. And what I've effectively done is undersize the expansion tank. And what could happen is when the boiler goes to fire and it goes to the high limit to the 180, 200 degrees, your relief valve could dump. And then you're going to look at the tank and say, hey, I got a defective tank. It might be just that it was undercharged. It wasn't charged properly. Something to be aware of. So when you get involved with expansion tanks, again, this whole thing about pressure reducing valves. Why a pressure reducing valve? Same as expansion tanks, set for 12. Well, most applications are a 2-story installation. So down from the basement, when I do the math and I get to the high point, what does it take to fill that system and have it under pressure? Well, generally speaking, over the years, they established that they really needed about 8 pounds from the basement to the highest piece of radiation in the second floor. And then what the industry standard was, always add 4 so that you had positive pressure at that high point. If you just filled it at 8, you would have water up there, but the water would be at 0 PSI. If I had a float vent on a piece of baseboard or what have you, and I'm at 0 PSI on the water side, and I'm venting to atmosphere, which is 0 PSI G, I have no motive force. So by adding that 4, I had positive pressure. So whatever it takes to get to the height, so right over here, this little statement, it is a function of the static height of the system. Whatever it takes in feet, so to calculate the required fill pressure, divide the number of feet from the fill valve location to the highest point in the system by 2.31. And what you're doing is you're just converting feet into PSI, because that's typically on the gauge that you're going to look at downstairs on the boiler. They're typically listed in PSIG. So whatever it takes in feet of height, divided by 2.31, right over here, and then to that number, add 4 PSI for positive pressure. That's it. Now that number now becomes your pre-charge for your diaphragm tank or your bladder tank. So here's just a quick example of saying, hey, we got 30 feet. So I do the math and it says, okay, 13 PSI to get to the high point, then add my 4 pounds of positive pressure. So 13 PSI plus 4 PSI, I would want to set that PRV to 17 PSI, as well as pre-charge. Well, in this case, they're showing a steel tank, but if I had a diaphragm tank, I'd pre-charge the tank to 17 as well. So you have this pressure band, and that's kind of the job of, or one of the jobs of the expansion tank, whether it be a diaphragm, bladder, or even the old steel, is you have this low pressure limit. And what is that? That's the PRV setting to fill the system with water all the way to the high point, and then have it under pressure, add 4 PSI at the top. And then I have this relief valve setting where it's there to protect. Typically, it's going to be a boiler. It could be a heat exchanger, but I have a relief valve. So one of the jobs of the expansion tank is to pre-charge the system, establish a low limit, which is your fill pressure, allow the pressure to rise in the system as the volume of water in the system is being heated. So the molecules are getting all excited and they're starting to expand, but have the tank sized properly so that I never get to this point of relieving the relief valve, having it open. Because opening relief valves, you know, of course, if it's needed, thank God it's there so you don't have a bomb on your hands. But every time a relief valve dumps, what you're doing is that when the system cools down, the pressure drops, this pressure reducing valve is going to respond because its diaphragm is going to sense a drop in pressure and it's going to add more makeup water. Problem with more makeup water is 1, it's cold, 2, it's expensive, 3, it has a lot of oxygen. That oxygen does a very good job of eating away at cast iron components and steel. So the idea of a hydronic system is it's a closed loop. I'm almost never adding makeup water. So after a certain period of time, that oxygen becomes inert. It's not aggressive. And I have a system that can last for a long, long time. So an expansion tank's job is very important in terms of a lot of things, but one of them being the integrity and the life of that closed loop hydronic system. So real quick, a question, we talked about it extensively on a seminar a couple of weeks ago, circulator expansion tank location, does it matter? I can't get into talking about expansion tanks without sharing a picture of my good, not a friend, I guess, I wish he was, but he had passed away before I got a chance to meet him, but Gil Carlson, talking about, you know, point of no pressure change, and it's all a function of the expansion tank. So that's another job of the expansion tank, is it's a pressure reference point for all of your circulators. So if they're on the supply or on the return, they're going to react differently. So I apologize, I'm not going to go in deep detail this morning because we're really here to talk about the actual sizing of how do you get to the right size tank. But this is the picture that Gil used to educate the industry, starting with the engineering community, then branching out to the contractors and the wholesalers, et cetera, about when you turn a circulator on, how does its pressure differential impact the system's fill pressure, its static pressure? Is it a positive or a negative? And it was all about the location of the expansion tank. In this case here, he's showing an old steel compression tank. It could very well easily be a diaphragm or a bladder. Real quickly, what they're showing here is when you pump away from that point of no pressure change, when you turn the pump on, his pressure differential is additive, so it's a positive. So every point along your hydronic system, its pressure increases. Naturally, as you get further and further away from the circulator, that increase is less because the system's eating up that pressure differential that the pump developed. Why do I have pressure differential? I need that to move the GPM, right? We talked about that in another class, the flow rate to provide the BTUs to the radiation where the people live. So as I move the water, there's frictional resistance. I need to overcome that. That's established by, or overcome by having the pump be sized properly to provide the proper differential. The point of this conversation this morning is always try to pump away from the expansion tank. When you pump away, it increases the pressure above the non-operating. And what they're saying here about keep that section short, what they're referring to is the closer you can get these circulators to that point, the better off you are. If you pump on the return and you pump towards an expansion tank, all of the differential that that pump can develop shows up as a negative. So I've negatively reduced the system's pressure effectively throughout the whole hydronic loop. So it's not that the pump can't still operate. It can. It'll create a differential and the circulation will take place, but you've negatively impacted the system's fill pressure, which could have a lot of crazy impact outcomes. So subtracts some portion of pump head from the non-operating, the fill pressure. If you have a pump that's big enough, you could boil the water. You could lower the pressure so much that you could create a partial vacuum. Air could be drawn in. And actually, really severe enough, you can actually cavitate a pump and damage it. So let's get into sizing expansion tanks. Kind of a visual here, but it's saying, look, if I had 2,000 gallons of 40-degree water, and because water is not compressible, and I heated it to 180 degrees, so I have this expansion factor, I would have an additional 56 gallons of water. And I have to put that water somewhere because based on this statement right here, water isn't compressible. I have a relief valve that's going to do its job and it's going to relieve. And thank God it did, because if it didn't, I have a boiler that could potentially explode and become a bomb and really hurt someone or kill someone. So I want to have a place to accept this expanding 56 gallons of water. So there's these charts, and nowadays I'll show some quick examples. When we use software, these charts are kind of incorporated in the development of the software that we use on a day-to-day basis when we're asked to size expansion tanks. But what it's saying here is volume expansion in percentage based on initial 40-degree water temperature. So when I fill the system from the street water, they're making the assumption I'm starting at 40 and then I'm going to a certain temperature. So over here, if I went to say 200 degrees, it's saying it's about 0.03, 3.5%. So 3%, 4%. So somewhere in the middle there, 3.5%. So whatever volume of water I have, which is an important factor in sizing expansion tanks, we're going to talk about, I'm going to multiply that volume by this expansion factor. That's going to tell me how I got from 2,000 gallons to 2,056. That's a very important piece of the information, because that's going to influence how do I size and what tank do I buy. So kind of some basic relationships. Boyle's law. What it's referring to is before we heat the water, we have a certain pressure in volume divided by temperature. We're making the assumption that the tank temperature stays the same. So they try to thermally isolate the tank so it doesn't see that warmer water. And then when I heat the water, my pressure is going to change, which means my volume is going to change. Or my volume is going to change, which means my pressure is going to change. But it's all based on this Boyle's law. So when you get involved with sizing expansion tanks, there's actually a formula behind the scenes. And what it's talking about is here's our net expansion factor time times our volume, our system volume. And then we're going to take that and we're going to divide that number by atmospheric pressure over fill pressure and atmospheric pressure over what's my relief valve setting. You know, and typically it's usually 10% below that. We might not factor that in right now this morning, just doing some numbers, doing some calculations. But it's atmospheric pressure over fill, atmospheric pressure over relief valve. So DT, expansion tank size in gallons, BS, volume of the system. That's probably one of the most important numbers, and at the same time can be one of the most elusive numbers to gather. Net expansion of water, pressure in the tank before the water enters. That's the PA. And then the PF is your fill pressure, and PO is your final tank pressure, which they're making the assumption the tank a lot of times is going to be down in the mechanical room right near the boiler, right near the relief valve. Again, we just talked about that. So if you look at in the industry, it's not uncommon when you're talking to guys, they say, hey, I got a 200 or 150,000 BTU heating system. I need an expansion tank. And what would happen is over the years, the expansion tank manufacturers would make these charts, these tables, and they would start with a BTU rating. And then they would say, here's the model number that you need. So a lot of times in the industry, the guys would say, okay, whatever the BTUs are, that's the expansion tank I need. And that's can't be further from the truth, but I understand why they did it, because that's a pretty nasty formula to be working with. That's pretty challenging. So they come up with these charts, and what they did is behind the scenes, they would then go out and calculate, okay, what's the water volume in a typical 150,000 BTU system? Well, they would start with and say, okay, 150,000 BTUs on a typical heating application's probably going to represent 15 gallon a minute based on a 20-degree delta T. That being the case, 15 gallons a minute, I probably have 1.25 inches, maybe 1.5 inches pipe. How big of a system, how much water would be in there, what type of radiation am I using? And that's why when you look at these charts, 150,000 BTUs, and I can use an HFT 30, which is B&G's, typically pretty small standard tank. Notice that the same when you're connecting it to baseboard. If I have the same 150,000 BTU boiler, but I'm connected to maybe convectors, they're saying that tank's probably too small, I need a 60. If you're connecting to cast iron radiators, 150,000 BTUs worth, I need to go all the way up to a 90. So what's the difference between these? Well, it has to do with system volume. That's the biggest difference. The other little out, if you will, that is kind of, if you're going to use a chart like this, you got to make sure I'm in a 2-story building, I'm filling it to 12 PSI, my boiler has a relief valve of 30, and the average system water temperature is no hotter than 200. As soon as I go to a different house or a different building where maybe that 12 PSI is not adequate to fill the system, this chart's useless. So here's just a picture of some of B&G's expansion tanks, diaphragm, if you will. Standard factory pre-charge, like we talked about earlier, comes at 12 PSI. Here's a specifications, if you will, of the smallest one all the way up to the largest unit that they offer. I just want to focus on this area here for a second. Tank volume and acceptance. Those are the two things. These tanks aren't full acceptance, so the bladder can only go so far, and that references the acceptance volume. How much water do I have? What's my expansion factor? How hot's it going to get? That's the water that I have to accept into this tank. This is the total volume of the tank, and I have to match this criteria as well, so that my relief valve doesn't blow, the pressure doesn't build too much. So there's two factors involved in expansion tanks: the total tank volume, which keeps my relief valve closed, and the acceptance, which is the amount of water that's going to expand into that tank when the boiler is fired. This is a great picture of what's going on inside a tank. So if the net expansion is 3.5%, that's based on 200-degree water, and the system contains 500 gallons of water. All it is math. Sorry. Take 0.035 times 500 means that 500-gallon system is now going to have 517.5 gallons. That has to go somewhere. That's the job of this tank. So I have, when the system's cold, I have a pressure and a volume of the air and the corresponding pressure in that tank. That's going to be my fill pressure. I don't want water in this tank until it starts to heat. And as it does, what am I doing to the volume of air? I'm compressing it. As I compress a gas, the pressure increases. So that's what we see. We registered on the gauge on the boiler. As you heat the boiler, you'll watch the pressure gauge climb. That's the water entering into this tank, squeezing this volume of air. This is a great, little visual. The job of the tank is to make sure the system stays within this allowable pressure rise. Don't blow the relief valve. So getting into some examples real quick. If I was referencing an old steel tank, this was the formula they would have used years ago. Over here on the right-hand side, this is my net expansion. How hot's the water going to be? What's the volume of the system? Divide that number by this. The atmospheric pressure, the pressure in the tank before water enters, over the fill valve setting. How tall is the building? Here's my atmospheric pressure again. And what's my relief valve? What's the final tank pressure? So to plug some numbers in real quickly, I have 1,000 gallons of water. Oops, getting a little jumpy here. I have 1,000 gallons of water. The average water temperature, mean water temperature is 180 degrees. I'm filling it to 12 PSI and I'm relieving it to 30. When I plug in those numbers of that formula back here, this is what it looks like. And it's just math. You just do it on a calculator. And the final result would say, hey, I have 1,000 gallons times 0.0279, okay, 27.9 gallons of expanded water divided by this factor here, which is referencing my fill pressure versus my relief valve pressure. I need a tank that has 126 gallons. That would support this application. 180 degree water, 1,000 gallons of water, fill valve 12, and the relief valve 30. Diaphragm tanks, the sizing formula, and this is where I want to focus for the remaining part of this portion, is it's a little different, and the reason for that is this. Pressure in the tank before filling is not atmospheric. It is pre-charged, like we talked about throughout this morning, pre-charged to the fill pressure. So this allows us to substitute PF for PA. So the formula over here changes to 1 minus my fill over my relief valve. This number up here still stays the same. How much water do I have? What's my expansion factor times my volume of water? And again, pre-charged, say the quick example here, they're showing 12 PSI. I really don't want any system water in here. As the water is heated and it expands, it enters in, it compresses the air here. That's the volume of that acceptance factor. They refer to it over here, acceptance volume, AE. So a diaphragm, real quick, 1,000 gallons, same thing. We'll do the same example. 180 degrees, 12 and 30. Plug in the numbers. I have 1,000 gallons heated to that 180, so it's the same expansion factor. And now I have a different formula down below. And when I do the math, it's saying I get two numbers now. And these are the two numbers that are important. This is the volume of water that's going to expand. So my acceptance factor, my acceptance volume on the tank has to be large enough. And my total tank volume has to be at least this big so that I don't build pressure higher than my relief valve and open it up. Another quick example, same system, 1,000 gallons, 180 degrees, but now I'm in a 3-story building instead of a 2-story. And when I do the math, I need about 14 PSI to get to the high point, and then I add that positive pressure of 4 like we talked about. So now I have a fill pressure of 18. So when I do the math, I do the calculation, well, if I happen to have the same volume, I'm going to have the same expansion, right? Same temperature, same volume. But now I have a different formula down below here. My fill and my relief are different. And you'll see that now I need not only a tank this big, 69 gallons, even though it has the same volume of water, but I have a different pressure setting. I need a 104-gallon total tank. The acceptance is going to be the same because the volume of water is the same and the temperature is the same. But my pressure ranges are different. So I'm going to need a bigger tank to keep my relief valve blowing. So here's a kind of a quick example, just throwing some numbers on. And I'm saying, okay, I'm 18 feet. I got 500 gallons of water. The temperature range is 40 to 200. When I do the math, my fill pressure is 12 PSI. My relief valve down here on this residential boiler perhaps is 30 PSI. I need an expansion tank. So I'm going to plug in some numbers here. I'm going to say 500 times 0.035 is 17.5. I'm going to plug in my relief versus my fill pressure versus my relief. I do a little math formula. I come up with an answer of I need a total tank of 43 gallons, and I need an acceptance factor, an acceptance volume of 17.5. So these two criteria I have to match to support this requirement over here. 500 gallons, 200-degree water, 30-pound relief valve. Now, modern day, how am I going to handle it today? I'm going to go the easiest way, and I'm going to share it with you guys afterwards with that follow-up email, is you go to FIA's website, fiainc.com. And on there, there's going to be a products page, a products drop-down page. Click on it, go to B&G. When you go to B&G, you go to their selection tools. One of the selection tools, the first one, it's very, very popular, is called System-Wise. And you can pick pumps, triple duty valves. In this case here, I have a screenshot showing an expansion tank sizing formula. So over here, what I'm doing is I'm showing a 40-degree fill temperature, a maximum temperature of 200, a fill pressure of 20 PSI. I'm just using water. I'm not doing glycol. My volume is 500 gallons. My relief, my maximum pressure is going to be 30 PSI. And look at it, it's coming out with the exact same numbers that we just showed doing the math formula. 43 and 17.5, 43 and 17.5. So this is a much quicker, obviously much easier way of establishing. But anyway, so moving forward, I go to a bigger system, a little taller. Now I got a fill pressure of 18 PSI, same volume of water, same temperature, relief valve 30, plug in my numbers. What is my answer? It turns out to be, I need a 65-gallon total tank now. Same acceptance factor because it's the same volume of water and the same temperature, but I need a bigger tank because my pressure on my relief valve when it's cold is already at 18. It's not at 12. So I only have a much smaller band allowable rise in pressure before my relief valve blows. So the way I get there is I need a bigger total volume, total gallon of tank to support the volume, temperature at a higher pressure. Again, just go to System-Wise on the Bell & Gossett selection tool on their website, plug in the same numbers. The only difference over here is the 18 PSI, and I spit it out. Sure enough, 65 gallons for total tank and acceptance volume of 17.5. And then what they'll do, I didn't show you last time, but they'll start listing model numbers, recommended model numbers that can support these two requirements, total tank and acceptance factor. I think I got one more example real quick I was going to show you is if I had, say, that two-story building, 12 PSI fill, but maybe the boiler manufacturer that I'm using just happens to ship their boiler with a 50-pound relief valve instead of the standard or more traditional 30. How does that factor in? How does that impact the requirements of our tank? Again, just doing the formula, or I'll show you the software. The result is I actually need a smaller tank. Same acceptance. Why? Because it's the same volume of water at the same temperature. So the expansion factor doesn't change. So I have to accept that 17.5 gallons. But I can do that with a smaller total tank. And the reason for that is I have a much wider pressure range. I'm only sitting at 12 here on my relief valve when it's cold, and I can have that allowable pressure rise all the way up to, just below 50 before it releases. So using a bigger relief valve, I can use a smaller tank. So it's something to be aware of. Again, go to the System-Wise software on the Bell & Gossett's website through FIA's products page website. And the only thing I've changed is my max tank pressure. I changed it from 30 to 50. And in doing so, it says, hey, 29.8, okay, 30 gallons. And here's my acceptance, which we already talked about because the volume of water didn't change and the max temperature didn't change. So my expansion factor didn't change, 17.5 gallons. So here's just one last quick thing to share with you. I'm in downtown Boston. I got a 5-story brownstone, Beacon Hill. I have a 13-foot 13-foot ceilings. I'm going to do the math. I'm going to say, okay, 65 feet to get to the high point. I'm going to have a fill pressure of 32 PSI. So I sure as heck can't be using a 30-pound relief valve on this boiler. So in this case here, the example is I got a 50-pound relief valve. So 32 initial, just to get it there and have 4 pounds positive pressure at the high. Same volume of water we're using, same temperature of the water. How does it affect the sizing of the tank? So again, doing the math formula, I need now that same system in terms of volume. I need a total tank volume of 65 gallons with an acceptance of 17.5, so that when I start at 32, I don't relieve that relief valve at 50 PSI. I'm just below it. And that will work. That will satisfy a 5-story brownstone. What happens if I was to put the tank at the high point of the system? Still seeing the rest of the, all the other conditions, but I physically just put the tank up here. What is my initial fill pressure going to be in that tank located here versus down more traditionally with an air scoop? And this is why sometimes you'll come across systems where they'll do something just like this. They'll have the mechanical room downstairs, the air separating device downstairs, but they'll run a line up to the attic and they'll locate a tank up here. So what we do is we apply the same math formula. But what's happening is now we're talking about what's the pressure on the expansion tank. And the pressure on the expansion tank is going to be 4 PSI at the high point. And then it's going to be an allowable increase of only 18 PSI so that I stay below my 50 PSI. So again, apply the numbers. And what you'll find is if you take that tank and you move it to the top of the highest point of the system, I only need a 40-gallon tank. I don't need a 60-gallon tank because I have less pressure on that tank at the beginning of that system when it's cold. So that's why the engineering community sometimes, what you might see is they'll locate expansion tanks just to make some of that equipment, the size of the equipment. Obviously, we're talking a fairly small system here, but the equipment can be smaller. And that's also the other reason why sometimes you might see an equipment room in a penthouse. Now, all of a sudden, you can get away with smaller relief valves on the boiler because it's not seeing the static pressure of the height of that building. It's only seeing the 12 PSI max at the high point. It doesn't even really need 12. It could be less than that. And then whatever the relief valve is. So that's the kind of the behind the scenes, if you will, of expansion tanks.